Today we're going to talk about equilibrium of a rigid body. Up until this point, we talked about equilibrium of a particle or point. In that case, all of the forces are concurrent. They go through the same point. And so in 2D, there are two equations of equilibrium. The sum of all the forces in the x direction is equal to 0, and the sum of all the forces in the y direction is equal to 0. When we talk about a rigid body, however, all of the forces are not necessarily concurrent, and they might cause a rotation about the body, remember, due to a moment. And so we need to add another equation of equilibrium, and that is that the sum of all the moments about some point is equal to 0. And that some point is an arbitrary point. It can be either on or off the body. And remember that the body in these problems is rigid. In other words, it doesn't smush like a foam when we apply a force. So essentially, when we're talking about a rigid body in equilibrium, we have three equations of equilibrium. We have the sum of the forces in the x direction is equal to 0. The sum of the forces in the y direction is equal to 0. And then the sum of the moments about some point, again, that can be a point on or off the body, is equal to 0. So how do we analyze these in 2D? The first step is to draw the free body diagram. And then we apply those three equations of equilibrium. The sum of the forces in the x direction is equal to 0. The sum of the forces in the y direction is equal to 0. And the sum of the moments about some point is equal to 0. When we solve, if any of the results turn out negative for a force or a moment, then we just know that the sense of is opposite to what we assumed in the free body diagram. It just goes in the opposite direction. So how do we draw the free body diagram? The first step is to draw the outline of the body, outline of the shape free from all of its constraints. And then we show all of the known and unknown external forces and couple moments on that body. So this will be all the applied loadings, reactions, as well as the weight of the body if it's included. And then we identify the known forces and the couples with the proper magnitude and direction. And for any unknown forces, we assume a direction, or we assume a direction for the moment. And then we establish our XY coordinate system and include any dimensions on the body that are needed for the analysis. Now notice that there is something new here that we hadn't talked about before, and that is reactions. So what are reactions? Well, they are the connections, really, between the body and the ground, or the body and another body. So we're going to look at these supports in free body diagram. These are essentially the connections, again, between the body and the ground, for example. So one of the types of supports would be a roller, and a roller prevents translation in one direction. So it prevents, in this case, translation going up and down this direction. The roller can still move this way. So the support or the reaction would be one reaction that is normal to the surface that the roller is on. The second type of support is a smooth hinge or pin. In this case, the body can't move left or right or up or down. It's prevented from translating in two directions. And so we have two forces that are reactions, a force in the x direction and a force in the y direction, because it prevents translation in two directions. The third type of support is a fixed support. In this case, this rod, we can't move it left or right, we can't move it up and down, but we also cannot turn it. This hinge, in contrast, we can rotate, but the support we cannot. It's fixed into this wall. And so the support prevents rotation in addition to translation in both directions. And so you're going to have reactions of a force in the x direction, a reaction of the force in the y direction, and a moment reaction. Okay, so the roller is going to have one reaction that is normal to the surface on which the roller is. A hinge, which can still rotate rotate, but can't move in two directions, will have an X and a Y reaction, and then a fixed support will have reactions in the Y, the X, and a moment reaction. So let's look at this beam that has a uniform beam that has a weight of 200 kilograms, and it is in a fixed support. This is a brick wall. So we're going to first start by drawing the free body diagram of that beam. So we're going to draw the beam separated from the support. The support is this brick wall. So there is my beam. I've included all of the known forces already. So we have the applied 1500 Newton force, as well as the weight of the beam. And since we know that it's a uniform beam, I'm applying that weight in the middle of the beam. Then I need to include my reaction forces that are going to replace this brick wall. So this is a fixed support. So I'm going to have AX, I'm just going to call it A, an AY, and I'm going to have a moment reaction. Now I have indicated each of these reactions, both in the forces and the couple moment, as positive. If any of them turn out to be negative, then I just know that the direction is opposite of what I have drawn here on the free body diagram. So this is the free body diagram. Once you have drawn the free body diagram, the next step would be to solve the problem. So there's my free body diagram. So now I have my three equations of equilibrium. So I can start with the sum of the forces in the x direction is equal to 0. And the only force that I have in the x direction is my AX. So immediately I know that AX is equal to 0 newtons. Then I can do the sum of the forces in the y direction is equal to 0. And I've established my bases as xy positive. So this would be negative 1500 minus 1962 plus AY. And solving that equation, I solve and get AY is equal to 3,462 newtons. So there's two reactions, and then to get the third one, I'll take the sum of the moments, and I can choose any point. I'm going to choose point A, and the sum of the moments is equal to 0. So first I have MA, which is a reaction at A. AY and AX both go through this point A, so that they do not cause a moment about A. So I do need to include the 1500, and that distance is 1.5. It's causing a clockwise rotation, so it will be negative. And then I also have the 1962, and its distance is this 2.5. It's also pushing down and causing a clockwise rotation, so it will be negative. So if I solve this equation, I get the moment reaction, MA, is equal to 7,155 Newton meters. And it turns out positive, so I know that I drew it in the correct direction, and the moment reaction is counterclockwise. So AY goes up, AX is 0, and the moment reaction is positive or counterclockwise. So again, draw the free body diagram, and then you apply your three equations of equilibrium in 2D. Now, I took this moment about A here, but I could have just as easily taken that moment about any other point. So for example, if I decide to take the moment about X, I can say that sum of the moments about X is equal to 0. And in that case, I still have MA, still positive, but now AY creates a moment about A, so that would be AY, which I know is 3,462 newtons. And its distance to point X is 1.5. It is pulling up, so it's tending to rotate clockwise, so this will be negative. And then I have the 1962. And the distance from the 1962, the perpendicular distance to the 1500, is the 2.5 minus 1.5, so that is 1. It is pulling down, so it's tending to rotate this beam clockwise, so this will be negative. And if you solve this out, we get MA is equal to 7,155 Newton meters. So we get the same thing. So it doesn't matter at what point you take the moment about. I could have just as easily taken it about this end of the beam here or here. You will get the same answer for the reaction moment. So let's look at another example. What are the reactions here at A? This is a bent beam with a fixed support at A. So the first thing we're going to do is draw the free body diagram. So I'm going to draw that beam, separate it from the supports, and then I will add all of my known forces and couple moments. So I've added the known forces and couple moments, and then I need to replace that fixed support with the reactions. So I'm going to create, if it's a fixed support, so it's going to have an AY and an AX, right? It prevents translation in both the X and Y direction. And then there will also be a moment reaction. So there's my free body diagram. If you don't get the free body diagram correct, then you're going to have trouble with the problem because you won't be solving for the correct reactions. But once you have the free body diagram, then we just come and again use the equations of equilibrium. So I can do again the sum of the forces in the x direction is equal to 0, and I have AX, right, if this is positive XY. So AX plus, I have this 150 pound force, and the X component of that will be 4 divided by 5. And then I have this 50 pound force, and we have 2 components of that, so that will be also in the positive direction, so 50 pounds times the sine of 30, and that will also be positive. So solving this equation for AX, I get AX is equal to negative 145 pounds. And so this AX here, instead of going to the positive direction, it's actually to the left, which makes sense because the 2 applied forces are to the right. Next, I can take the sum of, this should have been the forces here, not moment. The sum of the forces in the y direction is equal to 0. And I have AY. Then I take this 150 pound force, and the y component will be 3 divided by 5. It's pointing up, so it will be positive. And then the 50 pounds, and this component here will be the cosine of 30, and it is also positive, and so it will be pointing up. Solving this equation, I get AY is equal to negative 133 pounds. So again, I just have the wrong direction here. The AY is actually going to point down. And then finally, I can do the sum of the moments about some point, and I'm going to choose point A since both AY and AX go through that point. It's less math to do, I guess. So the sum of the moments about A is equal to 0. So I'm going to have the X component of the 150. So I have 150 times 4/5. And the distance of that component to A is 2 feet. And it is going to be pushing this way, so it's going to tend to rotate this thing counterclockwise, so it would be positive. Then I have this 500 foot-pounds. It is also positive, so it's going to be just 500. We don't have to multiply it by distance. It's a couple moment. It already has that distance. And then we have the 50 pounds. And we can take the y component of that, which is times the cosine of 30. And the distance from A to the line of action of that force is going to be 3 feet. And this y component is tending to rotate the beam here counterclockwise. Clockwise, so it will be negative. And then we also have the x component of that 50-pound force, so that'll be 50 times sine of 30. And if we draw the line of action of that, the distance from A to that line of action is 6 feet. And it's tending to push this beam, so it's tending to rotate it counterclockwise, and so that would be positive. And then we also have, almost forgot, the MA, which is what we are solving for. And if you solve this out, rearrange the equation, you will get MA is equal to negative 760 foot-pounds. So my reactions are the moment is negative 760 foot-pounds, so that just means that the reaction moment is going clockwise, not counterclockwise. AY is negative 133 pounds, so it's going down, and AX is negative 145 pounds, so it is pointing to the left. So draw the free body diagram and then apply the 3 equations of equilibrium. Okay, let's look at one more. What are the reactions here at A and at F? Notice here we do not have a fixed support, but the first thing that we need to do is draw that free body diagram. So I'm going to again start by separating that beam and adding the known forces, which are the 800 newtons at D and the 800 newtons at E. And then I'm going to replace this roller and fixed support with reactions. So the roller is going to have just a reaction that is normal to the surface. So this will just be an A, or we could call that AY. And then the fixed support will have 2 reactions because it's preventing translation in 2 directions. So I'll have an FY and an FX. We can call that AY. So I have 3 unknowns. I still have 3 equations of equilibrium, even though there is not a moment reaction. We still have 3 equations of equilibrium. So let's apply those 3 equations of equilibrium. I can start with the sum of the forces in the x direction, as I've done before, is equal to 0. And if we're assuming that this is xy positive, then we have that's going to equal negative 800 for this one, minus 800 for that second force, plus Fx. And so Fx is equal to 1600 newtons. And then, like we've done in the previous examples, we took the sum of the forces in the y direction is equal to 0. And in that case, I have AY plus FY. Well, I have 2 unknowns, so can't really solve that equation. So what I'm going to do then is take the sum of the moments about some point is equal to 0 and solve for that. Well, I'm going to choose a point where that either goes through AY or FY to minimize the amount of math that I have to do so that I only have 1 unknown in this equation. So I'm going to go ahead and choose the sum of the moments about F is equal to 0. And so I will have AY, the perpendicular distance from AY to point F is 4. So AY times 4. That's pushing up, so it's tending to rotate clockwise. So this is going to be negative. Then I have this 800 Newton force. The perpendicular distance from F to that force is 3.75 times 2, which is 7.5. And it's going to tend to rotate this counterclockwise, so that would be positive. And then we have the second 800 Newton force, and its distance is 3.75 from F. It's also pushing in this direction, so it's tending to rotate the structure counterclockwise, so it will be positive. And all of that equals 0. Fy and Fx both go through F, so they don't create a moment about F. And if you solve this equation, you get Ay is equal to 2250 pounds. We can then take this result and plug it back into this equation. So the sum of the forces in the y direction is equal to 0, and that's equal to 2250 plus Fy. And so we learn then that Fy is equal to negative 2,250. And this is newtons, sorry. This should be newtons, not pounds. And so we know that this one we drew in the wrong direction, and it should actually go down. So as a recap, if you are solving equilibrium problems for a rigid body in 2 dimensions, the first thing you need to do is draw the free body diagram. That means drawing the outline of the shape free from its constraints, showing all the known and unknown external forces and couple moments. That includes all applied loadings, the reactions, and the weight of the body if it's significant. And then identify the known forces and couple moments with their proper magnitude and direction. Establish your bases and indicate any directions that are needed for analysis. Once you have done that, you apply the 3 equations of equilibrium. That's the sum of the forces in the x direction is equal to 0. The sum of the forces in the y direction is equal to 0, and the sum of the moments about some point, doesn't matter what point, is equal to 0. And then just remember that if a solution yields a negative value for either a force or a couple moment, then the direction is just opposite of what you have drawn on your free body diagram.